All right, so I started the recording, so we're all set to go here. And let's see. The first thing I wanted to mention was I already said it before, but I moved the ellipse homework back a little bit to Saturday, so it's due Saturday at midnight. So I usually don't like to make homework due on weekends, but anyway, did this time since I'm moving it back. So don't forget to either finish that or remember that it's due on Saturday, right? So finish it on Saturday. And I posted a new homework here on lines because we finished talking about lines already. So we're going on to something else today. So I've got that homework posted. Now, I wanted to remind you that something I wanted to show you in homework, because this has been the source of mistakes, is sometimes questions like this, where they're asking you to enter coordinates of points. Sometimes they have already put the parentheses into the answer, so you don't have to include the parentheses. So, normally when you're, writing coordinates for points, you put parentheses there right around them, but that's already been done for you in certain web-assigned problems, but not in all of them. So you have to look kind of carefully about whether you're going to add the parentheses or whether they've already been put. So, and if you do add the parentheses, it will count it wrong. So, so be careful of that, just in general, in WebAssign. Now, lots of you emailed me with extension requests. I think I granted all of those, but if you wait until just after the due time, then like after midnight, or you can wait till the following day, you can make an automatic extension request, and then I don't have to approve it. Okay, so it will just automatically get approved. So, but I think you have to do that like the day, maybe within 24 hours of the original due date, okay, or due time, right? And then you'll get an automatic extension. So you don't have to email me. So you don't have to send me the email prior to the due time. Okay, wait until afterwards, and then it will happen automatically, and then I don't have to. You don't have to wait for me to approve it. Okay. Now on that homework that was due on Monday, so the participation was good. We had a few people that didn't work on the homework. There probably were various reasons for that. Maybe some people were not able to get registered in time. And then, but in general, a large majority of the class participated in homework. If your grade there was, in the, I would say below 60, especially, then it would be really beneficial for you to, go ahead and make the extension requests in cases like that, so you can continue to earn points right after the due date, because you really want your homework grade to be as high as you can make it. So even if you were in the 70s, that's a passing score on the homework, but on homework you should really be aiming for a higher than in the 70s. You want that homework average to be really high, because that can really contribute to your final average, right? So as I mentioned at the beginning of the class, you can't always control easily your test scores. You can prepare, right? Of course you should prepare, right? And that will make your score higher, but sometimes things happen on the test, right? You blank out on certain questions, or you make some sort of silly error. There's no chance to correct it, right, until after I've graded it. So but on the homework you have a chance to correct things, right? So so you should really aim to be getting your homework scores high, since you're likely to be able to do that, right? And then that will really help your average at the end of the semester. In addition to, if you have a high enough homework average, you earn some flux dollars for that, right, at the end of the semester as well. So unless the homework is really impossible, and you did your best, but you couldn't bring your score up, then maybe try for getting your averages into the 80s and the 90s on your homework, right? Your scores in the 80s and the 90s on homework. I think in most homeworks that's possible to do that. Now, I also wanted to, and you've also been emailing me very well your questions from the WebAssign with using that Ask Your Teacher or Ask Your Instructor button. So that's great also. Sometimes though, the questions are of sufficient complexity that it's hard for me to respond through that, just through typing, right? Okay, it's something that I'm going to have to explain to you. And then, we can discuss that in class. Or I wanted to remind you though of the Math Center, right? So you have the Math Center available to you, which is in 925 North in the one main building. And they're the hours, and you can have walk-in tutoring there, so you can ask questions there 9 to 7 Monday through Thursday and 9 to 3 on Friday and Saturday. And you can schedule online appointments as well. So if you want to schedule an online session with a tutor, you can that too. Okay, so there's another place to get your questions answered. Okay, you also earn Flux dollars for visiting the center. Okay, so you can earn $2 per week, not per session, but per week there. If you visit the center, so and you check in there, so I'm going to know. I get a report there on your attendance, so that's how I add. That's how I add the Flux dollars. Okay, so just another resource there for you. All right. All right. So I think those are all the things I wanted to say. Almost. Do y'all? There's one other thing I want to mention, but do y'all have any questions immediately here? Huh? About something? Don't forget that last problem on the ellipse, the one about the planet orbit. We talked about that in class last time. So that's in the Zoom lecture. And it's also somewhere in one of the notes, but you have to kind of look. It's at the bottom of one of the sets of notes. So you have to look all the way to the bottom to see what I wrote down. Yeah.
I used to always tries.
Okay, let me see if I can do that. Okay, yeah, I can't unfortunately I cannot do individual problems, so I have to, it's a global thing I have to set, but
don't stress yourself out too much.
Okay, well, no, I don't mind adding some tries there, especially if it's not that big. Yeah, the reason I don't give unlimited tries is I do want you to there's a reason for that. I do want you to try to focus and concentrate and think about your work and try to do it in the given number of tries, not just be sort of randomly answering and I'll see if this works, right? Okay, but sometimes you do get desperate and you do get to that point where you're just like, I want to see if this works, right? Okay, right. When you've done it when you've done it several times already. Okay, I understand that impulse too. All right, but there is a reason why I don't give infinitely many tries. Unfortunately, in WebAssign they won't let you. There's a little bit of a flaw in the system. In some other homework systems, if you run out of tries, you can ask for a similar question. Since these questions are algorithmically generated, you can ask for a similar question and then kind of start all over with from scratch, right? But unfortunately, WebAssign doesn't do that. So that's just kind of a no, just restart that problem. Yeah, you can just ask for a similar version of that problem. It'll give you a new version of that problem, and then you can. Yeah, but that the website is what now? Oh yeah, well yeah. So you do have a in the help you have a similar question, right? But on some homework systems, after you run out of tries, you can say, okay, give me a new version of this question, and then you can start trying all over again, right, until you get it, right? But WebAssign doesn't do that. Once you're out of tries, your questions sort of out. Okay. Now, Oh, one other thing I do want to say about website is the help is really great. Okay. So I know there are like similar questions, and sometimes there's videos with certain questions, although the videos are pretty concise. So they're not always perfect, but yeah, I mean, they just say it in a very short amount of time because they're trying to make the video short. But so that's great. And I want you to make use of the help, but I don't want you to become over reliant on the help, right? So try to do the problem on your own without using the help as best you can, okay, before you use the help, because of course, you do not have the help available on tests. So if you become sort of addicted to the help, then you're going to run into problems with that on tests. Yeah. No, I don't think so. Yeah, no, you can request the help, and so you can look at the help first, but I would say try to not do that. Okay, so try to do the problem as much from recall of examples in class, right, or what we've talked about in the class as you can. Correct. That's the proper strategy for it, which is one of the reasons why we have the recall practice in class. But we don't have a recall practice today. Yeah, go ahead.
How many times would have exact till it runs out?
The sort of the standard number is 5, but I think on some homeworks it may be set to 7. So but usually on most homeworks it's set to 5. So if you're counting, when you get close to 5, it's time to slow down and either think carefully about the problem or seek help, right? Okay. So you might text me, through ask your instructor, and then I might say, well, we're going to have to show you this in class, in which case you would just have to sort of abandon the problem temporarily until we had a chance to discuss it. Okay. Now, one thing I do want to show you, though, that is important is on the Blackboard page, the sample test for test number 1 is here. Okay, so it is posted. So if you go to the Blackboard page and for the class, right, and go to sample test section, then there it is. So there's the link. Now, when you open this, you're going to freak, okay, because you're going to think this is way too long. No, this is practice, right? So this is not indicative of the length of the test. Okay, right. I just try to include a lot of different problems for you, okay, so that you can have plenty of practice for the test and understand what test questions look like, okay, what they might look like. So don't freak out about the length. And also some problems, well, a lot of it's blank space, so it appears longer because I put space in for graphs and stuff like that. So another thing is, so the test will fit into the length of time that is available. Okay, so I promise you that. And actually, when we come to take the test, we will take the test in 2 different shifts. So some of you will take it for the first hour, and some of you will take it for the second hour. All right, that's just for us to maintain social distancing. So and I'll tell you all more about that. Oh, by the way, remember, guys, if you have been going online, right, then but on the day of the test, you'll have to be here physically. Okay, that's one day you definitely have to be here. Some other problems are marked with a diamond. You see those? So those are kind of like extra. So if you're going through the practice test, you may skip those on the first, especially if you're limited for time working on the practice test. You may want to skip those first time through, okay, and then maybe come back to those. All right, so those are just a little bit deeper and maybe less important to focus on for tests. This is like this one. There's a homework problem exactly like this one. Okay, but I marked this as a diamond because I thought it was a little bit less important. All right, so so you can avoid the diamond problems first and then maybe come back to those unless you got plenty of time to work on everything. Oh, there's another diamond problem. Oh, looks like a problem Amanda was just asking about, right? Okay, there's something, in this case, it's a monitoring station orbiting a black hole, but the physics is exactly the same. All right, well, kind of, because black holes have kind of funny physics, right? But we're going to pretend that is the same. All right, so see, this is rather lengthy, and I'm not quite certain now where we're going to be in the notes when the first test comes up. So we may not get to all of this. So, so probably you want to start at the top and work down when you're working on the practice test. But it is really important to work on the practice test as much as you can. I know you have homework to do as well, okay? But work on the practice test as much as you can, because this will really help you do well on the test. So the number one comment I get from people who, taking the course after they've taken the first test, and then and they always tell me, oh, I wish I had spent more time with the practice test. That would have improved my test score. And then on the second test, they don't make that mistake, and their second test score improves, okay? Even though the material is harder. So, so take as much time as you have available to you, okay, to work on the practice test before the test, right? So you will understand what the test is going to look like and what the expectations are for taking a pencil and paper test, right? Since doing things in pencil and paper are not on the website, right? Okay. So there's my warning. That's going to go in some ears and out some ears. All right. But the ones who take that seriously will that will improve their test score. Yeah. No, the test will be like, yeah, the test is going to look like this. Okay. So it's going to be written. Yeah. And there will be virtually no multiple choice. There may be some odd question where a multiple choice is convenient, but that's not going to be the format of the test. It's going to be written. Yeah. Okay. The reason it's that way is because, well, I don't have a lot of faith in multiple choice tests, but I can give you extra credit, not extra credit, but partial credit, right? If I see your work. So that's really important. Partial credit is really helpful. All right. So there's the practice. It's ready. Our test is 2 weeks from today. It's scheduled to be 2 weeks from today. If we make any adjustments to that schedule, of course, we'll discuss those, right? Okay. But it's up there on the blackboard, so you can start playing with that. All right. Okay. And remember, you will be here on the day of the test. So that will either be that Wednesday, or if we postpone the test, maybe slightly, but on the day of the test, you have to come. Okay. All right. Oh, finally. All right. So we got through all that. Well, we don't have a recall practice today, so that'll save us a little bit of time. Let's jump directly into notes, the next set of notes. And so I mentioned last time that we're going to step back, and we've been talking about different types of curves, in this homework that's due now, it's ellipses, but we've talked about lines, of course. We have a homework for that, and circles, right? We've already done that homework. But we're going to step back a little bit and look at curves from a little bit more abstract viewpoint. As a mathematician would think of them. And this more abstract viewpoint is going to reveal some features of curves that allow us to distinguish between different types of curves. And that distinction turns out to be important for calculus. So what we're going to do today is going to feel very abstract, all right, but we're not going to do any proofs. So I don't think there's any proofs today. So you have that. Don't have to worry about proofs. I know those are challenging. Okay, but we do have some definitions. All right, so but the definitions are really very easy, because that's one of the great things about abstract mathematics is it's abstract, so it's it does make you think, but the concepts that you're working with are really quite elementary. All right, so that's the trade-off. All right, so first definition we're going to give you today is this one right at the top. In mathematics, a relation is any set of ordered pairs. Okay, so ordered pairs look like coordinates for points, right? Okay, you have two numbers in parentheses, right? Okay, and they have a particular order. You have a first number in the pair, right? The first coordinate, and you have a second number in the pair, the second coordinate. Okay, and right, that usually we call the first number in the pair the x coordinate, and the second number in the ordered pair we often call that the y coordinate. But x and y are kind of they're kind of tied to rectangular geometry, right? The rectangular coordinate system. And so, but relations really are not really tied to geometry. Okay, they're a more abstract idea. So, so I'm also going to call the first coordinate in the ordered pair. I'm going to call that the input, or the input coordinate, right? So I don't have to think of it as being on the x-axis. And the second coordinate, sometimes I call that the output coordinate. All right, instead of y coordinate. But frequently our ordered pairs are coordinates for points. Okay, frequently they are. All right, not always, but frequently they are. So x coordinate and y coordinate is also acceptable as well. All right, so a relation, but keep in mind here, a relation is a set, right? It's a set of things, right? It's a collection of things, and the things in the set are ordered pairs. All right. All right, now, once you have a relation, okay, there are two other related definitions that you can derive from the definition of relation, okay? And the first one is domain, all right? If you take the input coordinates, so remember, a relation is a set of ordered pairs, right? Okay, so in a relation, if you peel off all of the input coordinates, all of the first coordinates from your ordered pairs and form a set out of that, that's called the domain of the relation. All right. So, you really don't have a domain unless you have a relation, right? A domain is something that's associated with the relation. So you start with a relation, but if you take the set of all of the input coordinates, first coordinates, out of all the ordered pairs in the relation, that set of numbers, that set, by the way, is just going to be numbers, not ordered pairs, then that set of numbers is called the domain of the relation. And if you peel off the second coordinates, that set of numbers is called the range of the relation. All right. So these three, that's the third definition here. So these three concepts are all sort of tied together, right? If you have a relation, you can have a domain for the relation, or you will have a domain for the relation, and you have a range for the relation. But you don't have a domain and range without the relation. You have to start with the relation first. Okay? Let's take a look now at an example of a relation. And again, this is a very simple idea. Okay, so you know, the definition sounds like it might be intimidating, but it's a really very simple concept, right? So here's an example of a couple of relations. All right, so we have sets here, right? And so you know how we indicate sets in mathematics, we use these curly braces, right? Okay, and then inside of the sets are the inside of the curly braces are the objects in the set, the elements of the set. And remember, for a relation, the elements of the set are ordered pairs, right? So in this first relation here, right, it has 1, 2, 3, 4 elements, right? And it's these 4 ordered pairs. Of course, the ordered pairs I put in parentheses, like we traditionally put ordered pairs. Now, in in mathematics, we often like to give sets names. So I gave this first relation the name A, okay? But I could name it anything that I like. So when I write A equals that, I'm just putting the A there as just to give this relation, a name, so that I can call it by its name. And then the second set there, the second set of curly braces is another relation, right? This one has 1, 2, 3, 4, 5 ordered pairs in it. Okay. But because it's just a set of ordered pairs, then this is a relation. This relation I gave the name B. Okay. So I'm not very creative with my names there, just A for the first relation and B for the second relation. Now, a relation can be a set of ordered pairs of any size. So a relation can have infinitely many ordered pairs in it, but of course I'm going to have a hard time writing that down, right? So I picked just a couple of small relations here, one with 4 ordered pairs and one with 5 ordered pairs. Now, again, once you have a relation, right, then you can write down its domain and its range. So what's going to be the domain of the relation A? Right, yeah, just peel off the first coordinates, right? So the domain here for A is just this set. So I'm going to indicate that with the curly braces, right? And just what Amanda said there, -2, -1, 0, and you do not have to repeat the -2, okay? Because in sets, duplicate elements don't count, all right? So you don't have to repeat the -2. So your domain there is just -2, -1, and 0. What's the range of B? Yeah, you just peel off the second coordinates, right? In this case, we're talking about the relation B. So we get 4, 5, -4, and 7. And again, since this is a set, you don't need to repeat the 7. Okay. So don't have duplicate elements in sets. See, just very easy ideas, right? Now, of course, what the question here is, what does this have to do with curves, right? Because we've been talking about curves. So what does this idea of relation have to do with what does it have to do with curves? And then what I promised is this idea of relation is going to reveal some distinctions between curves that maybe we had noticed before, but we didn't have a way of discussing. All right. Here's how this distinction comes about. Okay. All right. So it's hard to see here. I mean, you're not going to notice this unless someone points it out to you. Okay. But there's a subtle distinction there between the relation A and the relation B. Okay, in their structure. All right. Now, of course, one difference is that they don't have the same number of elements, right? Okay. A has 4 elements in it. It's got 4 ordered pairs in it, and B has 5 elements. It has 5. Right. So that's one difference there between B. Okay. But there's another difference that's less obvious, and that's going to turn out to be useful to us and important to us. And here's the distinction. Notice that in the relation A, okay, we have 2 ordered pairs here that begin with the same input, right? These 2 ordered pairs begin with the same input. That does not happen in relation B, okay? In this relation, all the ordered pairs have different inputs, right? Okay, or all the ordered pairs have. That distinction is gonna turn out to be useful to us. All right. So let me see if I can express that. Okay. If you have a relation where each input is matched with exactly one output, in other words, don't have a repeated input coordinate in the ordered pair. Okay, such a relation is called a function in mathematics. So relation A here is not an example of a function, all right, but relation B is an example of a function. Why is relation A not a function? Because you've got that same input -2, right, matched with 2 different outputs. Okay, here -2 is matched with 3, here -2 is matched with 4, but that does not happen in relation. Okay, so A there, not a function, but B is a function according to this definition of functions. Let's practice that a little bit, but it's so easy to practice, right? Okay, so I wrote down here a bunch of relations. I wrote them as tables of pairs, so I didn't exactly write them down as ordered pairs, but it's clear that this table, you can think of it as a set of ordered pairs, right? Okay, because this first column in the table, you can think of that as the ordered pair 0, 0, right? The second column in the table, you can think of that as the ordered pair 1, 1, et cetera, right? Up to the last column in the table, think of that as the ordered pair 4, 4, right? So when we're writing down relations, we don't we have different ways of picturing relations. We don't always just write them down strictly as a list of ordered pairs. Okay, sometimes we put them in a different formats, like in this case, format of a table. All right, my question is about each one of these relations here is it a function? Okay, so all functions are relations. A function is a special type of relation. Okay, so not all relations are functions. Someone needs to, hey, Val, can you mute yourself there? Okay. All right. So what about A here? Okay, is that relation also a function? I try to make them tricky here to confuse you. Yeah. All right. So yeah, all we have to worry about is, do we have repeated input with a different output? Okay, so do we have the same input matched with different outputs somewhere in the relation? If that happens, then you do not have a function. If that doesn't happen, then you do have a function. Okay, so so here what's a little bit confusing is that the y coordinate is always the same as the x coordinate, right? The output is always the same as the input, but that makes no difference to functions. Okay, what we're interested in looking at is, do we have a repeated input with a different output, right? And well, none of the inputs are repeated here, right? You have 0, 1, 2, 3, 4, right? So none of the inputs are repeated. So this has to be a function by. Okay, so A there counts as a function. What about B? Yes, right. Okay, because it's got the same set of inputs, right? As B has the same set of inputs as A. What's the set of inputs called? Domain, right? Yeah. So what I could say is A and B here have the same domain. Since A is a function, then B also has to be a function, right? Okay. So it is. Now, what I was trying to confuse you with here is that I repeated the same output multiple times, right? In fact, your range there is just the number 4. That's the only thing in the range of this relation. But that doesn't matter at all to this being a function. This does count as a function. Right? What about C? Yeah, no. Okay. So, and what screws that up, of course, is these two columns, right? Okay. So in this relation C, right, you have, if I wrote this relation down as ordered pairs, instead of in this table format, you know, in this relation, you would have these two ordered pairs, right? But there you have the same input, right, with different outputs. You cannot have that in a function. So this is a perfectly fine relation. Okay, there's nothing wrong with this as a relation, right? It fits the mathematical definition of relation, but it's not a function because you got the same input matched with different outputs. What about D? I was trying to trick you here. Yes. Yeah. Okay. All right. Yeah, I just played a game there, right? Okay. You do have the same output, same input repeated, right? But not with different outputs. Actually, this table is redundant, right? You really don't need to even have that column in there. Okay, you already have the ordered pair 3, 0 in the relation, so you don't have to repeat that. Remember, relations are sets, so you don't have duplicate elements in set. So I shouldn't have had these two columns the same. But anyway, this is a function. All right. So in a function, you don't care about the output being repeated. That's not important. Okay, so the output can be repeated. It's just you can't have the input repeated with different outputs. Right. So this is not a function. but this one is a function, although I wrote it down in a kind of a bogus way, all right? Does count as a function. What now? Oh, the signature sheet. Yeah, thanks for reminding me. All right, so make sure you're signing in your spot, right? So you can look, previous pages, make sure where I told you some people have been signing in other people's slots. Okay? And sometimes that causes disputes in the class and it gets ugly, so try to sign in your own slot there. All right, now let's tie this back, however, to this idea of relations. Let's tie this back to what we've been discussing in the class so far, right? So here we have an equation with two variables, right? And we know that we can graph the solutions to that equation. And of course, that's going to give us some sort of curve. What sort of curve is that going to give us here, in fact? Around, yeah, this is a linear equation, right? So we're going to get a straight line here, okay? I claim now that this equation really is also a relation, or you can think of it as a relation, okay? Right? I mean, it certainly doesn't look like a set of ordered pairs, right? Okay, when you write down the equation, it looks like an equation. But why can we really think of that equation as being a relation? Okay, and it's just because we know that when we create solutions to this equation, we get ordered pairs, right? Okay, right? And so the set of solutions to this equation is really just a set of ordered pairs. It's a set of X and Y pairs, right? Okay, so really the equation really does match a relation, right? It really does define a relation, okay? And what does that relation look like? I can't write down all the ordered pairs, right? In this relation, I can't write down all the solutions to this equation, but we already solved that problem a long time ago, right? We said, oh, we're not going to try to write down all the solutions to this equation. Instead, we'll just make a picture of those solutions, right? That's the graph. So y'all told me the graph is going to be a straight line. Let's see, what's the y-intercept? This is in slope-intercept form, right? So what's the y-intercept here? 1. So I know it crosses the y-axis here at 1, and it has a slope of what? 2. So let's see, that tells me, the slope of 2 tells me if I start at this point, if I increase x by 1, what's going to happen to y? It goes up by 2, right? That's what slope tells you, right? It tells you the change in y when x increases by 1. So if you start here and increase x by 1, y is going to go up by that slope, which is 2. So y will go up to here, and then you can keep doing this, right? So if you increase x by 1, y will go up by 2, right? Okay, and so on and so forth. Notice, of course, all those points fall in a straight line, right? Okay, we knew that ahead of time. So if I complete the line, it's going to look something like this, right? So there's the graph of that equation. And notice that graph is nothing more than a big collection of ordered pairs, right? All the points on the graph is an ordered pair, right? Okay. And so that equation really does indicate a relation, all right? So, there's the big connection. Our equations with two variables, right, are really, they fit the mathematical definition of relation. They are really relations, okay? Now, all right, here's the next question. Is this relation a function? So someone says no. Who said no? Why did you say no? No, this one? No, I'm talking about this one. Yeah, that is a function. Now, can you tell me why though? So if I ask you for an explanation, could you say why? Yeah, I don't know what the vertical test means, Amanda. So you have to explain that to me. So someone has to explain that to me. What did you ask? Are you gonna say? Exactly right. Okay. Every input has only one output, or you don't have repeated inputs here, right? With different outputs. Okay. If you pick an X value, right? If you pick an X value, let's just pick this one. How do you find the matching Y value? From the picture, how do you find the matching Y value? So if I pick this X value, how do I find its matching Y value? From the picture. Yeah, you go up until you hit the line, right? Okay, so you go up until you hit the curve, right? And then you do what? Come back across and see what the matching y value is, right? Okay. Well, look, if you pick any x value, right, and you go to the curve, how many times are you going to hit the curve for any x value you pick? One time, just one, right? Okay, that's just because it's a straight line, correct? Right? So you pick any x value, could be way over here, right? Okay, you go up to the curve, you're only going to hit the curve once, right? So there's only going to be one matching y value. Or if you start here way over here on the left, right, go down until you hit the curve, you're still only going to have only one matching y value, right? Okay. Amanda, that's what you meant by vertical line test. Okay. What Amanda was saying is if I draw a vertical line, that's the same as picking an x value and going up or down to the line, right? Okay. So you draw a vertical line when you find the matching y value, correct? Right. And there's only going to be, for this straight line, there's only going to be one matching y value. Okay. So is everyone signed up already? That was fast. Okay. So indeed, this equation is a relation, and better yet, it is a function. All right. Okay. Each x input has only one matching y output. Now, I have a harder question for you. What is the domain here? So if you were able to, right? If you were able to, look at every point on this line, right? That's gonna be an ordered pair, right? Its coordinates would be an ordered pair. And if you were to peel off all the x coordinates off of every point on this line, what set would you get out of that? Yeah. It would be all real numbers, right? It'd be the whole x-axis, wouldn't it? Right? Okay, right? Be the whole x-axis. This line goes, indefinitely to the right. It also goes indefinitely to the left. I can't draw the whole line, right? But right, in your imagination, it goes indefinitely to the left, right? Okay, so you can really, have any x value, right? You can really have any x value along the x-axis as a first coordinate in some point on this line, right? Okay, just pick anything on the x-axis. Of course, go up or down until you hit the line, right? And there's going to be a point in your relation, right, that has that x coordinate. So your domain is going to be the whole x-axis, right? All the way from minus infinity. Remember, there's our symbol for minus infinity, minus with that sideways 8, right? All the way over to positive. That's better known as all real numbers, okay? The x-axis is just a real number line, right? So your domain is all real numbers. What about the range? So what y values would you get from points on this line? I think the same, right? Okay. Because that line goes infinitely up and infinitely down. So if you were to pick any y value anywhere on the y-axis you want, you could find a point on that line that has that number as its y coordinate, correct? So your set of outputs there, your set of y coordinates is also going to be the whole y-axis, which also is a number line, right? Okay. So your range here is also all real numbers. We'll learn different ways for writing down all real numbers, but I like to write it out in words a lot. So there it is. Okay, finally, now let's look at f. Okay, so there's another equation with two variables, right? So this also, just like E, just like the line, this equation defines a mathematical relation, okay? Because the set of solutions to this equation is a set of ordered pairs, okay? So x squared over 49 plus y squared over 16 equal 1. That is a mathematical relation. My question is it a function? So to help answer that question, let's look at the graph of the solutions. What does the graph of the solutions look like? Do we know? It's not quite a circle, Evan. What kind of curve is this? That's an ellipse, right? Okay. This 49 is, of course, the same as 7 squared, and 16 is the same as 4 squared, right? Okay. So if we to plot this, let's see. It's going to be elongated along what axis? The x-axis, and the vertices will be at plus and minus 7, right? 1, 2, 3, 4, 5, 6, 7. Wait, did I count right? 1, 2, 3, 4, 5, 6, 7, right there. And then 1, 2, 3, 4, 5, 6, 7. Back here is the other vertex. Somewhere along the x-axis are the 2 focal points. I really don't care about those in order to make this graph, though. What about the y-intercepts? They're going to be at what? 4 and minus 4, right? So up here at 4 and down here at minus 4. So that's enough for us to draw, our, kind of okay ellipse, right? But drawing freehand on this computer screen is really, the screen has a very slick surface on it and doesn't give me any friction at all, so it's hard to write on. One thing I don't like about this computer. Oh, this side a little cleaner. Yeah, that looks better. All right. Well, anyway, there's the ellipse. All right. So pretend that's a nice, perfect ellipse there. And now looking at the curve, right? Is that curve a function? So yeah. So Ravi, you say no. Why? Yeah, there are inputs, right? In fact, there are a lot of them, but there is at least one, right, input where you have 2 different matching outputs. Can you tell me one? Can you give me a specific example? So what's an input that has, yeah. Ah, perfect, right. Yeah, if you pick X to be 0, right? If you pick X to be 0, you're going to have 2 different matching outputs, right? One of them up here at 4 and one of them down here at minus 4, correct? Okay, so what that means is the ordered pair 0 and 4 and the ordered pair 0 and minus 4, 0 and minus 4 are both part of this relation, right? Those ordered pairs are both in that relation. That relation has lots of ordered pairs in it, the whole ellipse full of them, but these 2 at least are also in that in that relation, and that can't happen in a function, right? Okay, because you can't have the same input with 2 different matching outputs. So in Amanda's terminology, we would say this fails the vertical line test. Why, Amanda? Because if you draw a vertical line right here at the y-axis, the y-axis is a vertical line, by the way, okay? So there's a vertical line, the y-axis, and how many places does it touch the curve? No, not everywhere, but twice, right? Yeah, here and here, okay? That happens lots in the ellipse, right? Okay, because the ellipse is this closed loop, right? So in fact, if you pick almost any x value, right? Okay, there's another one, that's 5, okay? If you pick almost any x value, you're gonna have 2 different matching outputs, right? But one positive and one negative, okay? So not only is this not a function, it's far from being a function, right? Okay, almost every x input has 2 different matching outputs, right? Okay, so that's way, way far away from being a function. So really quickly there, just really quickly there, how can you, just from looking at the graph, how can you sort of distinguish functions from curves that are functions from curves that are not functions? You can't have any sort of loops, okay, like this in a function, all right? Okay, so a circle also is not going to be a circle, also not a function. For the most part, in calculus, you're going to restrict your attention to curves that are functions. All right. So with some exceptions, you'll only be considering curves in calculus that are functions. Right. They simplify matters greatly. Okay. In lots of respects in calculus. So we often restrict our attention to just functions. They also have practical importance as well. Why functions are kind of the primary sort of relation that we like to think about. Doesn't mean ellipses aren't useful though. Okay. All right. Oh, I didn't write down what the domain and range were here. So what is so this is a relation. So it does have a domain. Okay. Even though it's not a function, it does have a domain. What is the domain? Yeah, that's right. It's numbers from -7 to +7, right? Okay. Any x value between -7 and +7, right? You can find a matching y value, right? Okay. So your domain would be all numbers from -7 to +7. The way we could write that down in easily mathematically is by using what's known as interval notation. I know you're familiar with interval notation. So this set of numbers from -7 to 7, we can indicate that easily just by putting the boundary values of the set, -7 and 7, write those down, separate them with a comma here, and then you will enclose them in this case, in square brackets. The square brackets indicate that -7 is part of the set and +7 is also part of the set. If you wanted to leave off one of the boundary values, put a parenthesis beside it instead of a square bracket, okay? That means that that number is a boundary value for the set, but is not really part of the set, okay? Sometimes that's a little bit confusing. This notation in this expression in mathematics means two different things in two different situations. You could think of that as being an ordered pair, right? So that could be the point -7, 7. This is also, you can think of this as the set of numbers from -7 to 7, not including -7 and not including 7. So that's one place. There are others where a mathematical expression is ambiguous. It's going to have different meanings in different situations, okay? But this is the correct domain, not one of these two. What about the range? -4 to 4, right? Let's look at the y values there. That would be ordered pairs in this relation. That would be -4, 2. You can't have something in your domain bigger than 7. If you came out here, for instance, to 10, right? And you're thinking, is 10 in this relation? Well, so there's 10 on the x-axis, but if you go up or down, what never happens? What do you never touch? Never touch the curve, right? Okay, so you never get a matching y coordinate for x equals 10. That's why 10 is not in the domain. Same thing for if you pick a y value bigger than 4 or smaller than -4, say 6, you try to find a matching x value for that, right? Go left or right. That never happens, right? You never touch the curve. So none of the points on this curve have a y coordinate bigger than 4. So let's look at kind of a very this is a very typical function in calculus. All right, so this is a pretty standard example of a function. There's its equation, y equal 2x squared plus 3x minus 1. So you know immediately that's not a straight line, right? If I were asking you, what does the graph of this look like? Well, you might not have a good idea, but you would know the graph is not a straight line, right? Because why? Yeah, because of the x squared, right? Remember, in straight lines, your variables x and y must be raised to just the first power. So here we have x squared in this equation. So this is not going to be the graph of a straight line. Here's what the graph actually does look like. So when you graph it, you don't get a straight line. You do get a curve, right? It's got a bend in it. Okay. It does have a bend in it, but it doesn't have loops like this. Okay. Does not have loops like this, right? You have a loop like this in your curve, it's not going to be a function. All right. So you can notice here, right, quite easily, if you pick an x, right, if you pick some x here off of the x-axis to find the matching y value, you're going to go up or down. In this case, we would go down, right? And how many matching y values are you going to find? Just one. Right? So that a relation is a function. There's what the graph of that equation looks like. Now, when you're dealing with a function, there's a special notation that we use with function called function notation. This only applies, however, to functions. So we do not use this notation with relations. Okay. Now, function notation looks pretty innocent when you see it. Okay. Once you get used to using it, it's very easy to use. So it's not really a difficult idea. But it really was a revolutionary idea in mathematics. Okay, function notation was developed in the 18th century, the 1700s, and really was, believe it or not, it seems like a very simple thing, but it was really a real breakthrough in mathematics that allowed mathematics to develop much more fully after function notation was developed. All right, so here's how function notation works. Okay, of course, in this equation, right, you have the two unknowns. All right. In function notation, we're going to replace the output variable because y is associated with the output coordinates, right, in our ordered pairs. We're going to replace that output variable y, all right, with the following expression. All right. So I'm going to put here. I'm going to give a name to the function. All right. So you have to pick a name for the function itself. So think of, I used f here for function, but you can use different letters. Think of f as being the name for this curve, okay? Name for this curve. And then inside parentheses, after the name of the function, we're going to include the input variable, okay? But that doesn't look very extraordinary, right? Remember, though, this is a replacement for y. So when you see this expression, it's just a replacement for the variable y. That means the same thing as y. Okay. Now, that looks like what? That looks like multiplication, right? But that's not multiplication because f is not a number. Okay, f is not a number. X represents a number, but f is not a number. So this is not multiplication, right? F is the name of this curve. So don't read that as f times x, all right? Because this is not multiplication. The way you read this properly is f of x. We have to read it some way off of the page. So that's the way we read it. But don't say f times x because that's going to confuse you. Okay? I know it looks like it could be multiplication, but in this context, since f is not a number, it's not multiplication. So you read that as f of x. But again, what that indicates is just the that's just a replacement for variable y. That means the output. Okay. Now, why is function notation useful? Okay. So let's look at this expression. So this is an example of function notation. But what I've done here is I've replaced the variable x with a specific value for x. In this case, -2. -2 is part of my domain, right? So it is appropriate to put -2 in for x. -2 is part of the domain of this function, right? So how do you read that? Off the page, what do you read? No, it's up there. Robbie, so what do you say, what? F of minus 2, right? Okay, so you read that as f of minus 2. Right? That's the way you read it. But what is the meaning of f of minus 2? Remember, the function notation was a replacement for what? The y, right? Okay. In fact, why don't we just write that? Okay. Yeah. The function notation was a replacement for the y. All right. So f of minus 2 is a y value. It's an output value. Okay? Now, which output value is it? It's the output value that matches minus 2. Okay. So let's write that out in words. Right. So this is the output y, right, that matches x equals minus 2. In that sentence really tells us why function notation turns out to be so important. Okay, because this notation, right, means all of this. All right, so that is a really great shorthand there. Okay, if we write f of minus 2, right, what we really indicated here is the output that matches the input x equals minus 2. Right, that's a lot to write down in English. Okay, but here we've written it in this very compact mathematical notation. All right, now that's what f of minus 2 means. Okay, it's the output that matches x equal minus 2. What is that number? Okay, what is the output that matches x equals minus 2? Well, we could try to figure that out from the graph. Let's see. Here's the graph over here, right? So there's minus 2. So if I go up, I'm going to come to somewhere up here, and then I'm going to go across, and it looks like it could be what? 1? But that's really kind of awkward to try to read that off of the graph, right? So what's our other option here to figure out f of minus 2? Yeah, that's right. You've got the equation, right? Okay, so you've got the equation there, so you don't have to read the graph, right? You can use the equation. Let's see, did I read the graph right there? Well, let's see, f of minus 2 would be 2 times minus 2 squared plus 3 times a minus 2 minus 1. Is that right? What is that? This is 2 times 4 minus 6 minus 1. Oh, yeah, that's 1, isn't it? Okay, that's 8 minus 6 minus 1. Oh, it is 1. Okay, so we read the graph right. Okay, but we don't have to read the graph because we have the equation, right? Okay, so we know that f of minus 2 is equal to minus 1. When you are, so this is called function notation. So when you're given function notation, there's a couple of things you can do with function notation. One of is evaluate function notation. That is, remember, function notation indicates a y value. So if you find the value of that y, like we did here 1, that's called evaluating the function notation. But if you explain what the function notation means in words, that's called interpreting the function notation. Both of them are really important skills, all right? So explaining in words what this notation means, that's called interpreting. And then telling me what the value of this expression is, that's called evaluating. So we did them both here. Let's try this. Let's try this again. So we're just practicing here with function notation. Okay. So let's try first interpreting this expression. So just explain what this expression means. By the way, how do you read that expression? Interpreting is not the same as reading it off the page. So if you read that off of the page, how do you read that? F of A, right? Okay. So make sure you can read the expression properly you read that as f of a. So I'm just trying to, I don't want you to say f times a, okay? That's what I want you to avoid, all right? Sometimes students just say fa, okay? That's better than saying f times a, but still not, all right? So you should read that as f of a. Now, what does that mean? So what does that expression mean in words? You write down the meaning in this case, it's going to be a little bit kind of weird, but let's write it down. So this means what? The output, right? That does what? That's right. The output that matches the input A. Or you could say the input X equals A, but we can just leave the X equals off, okay? We already said input, so we know that's X, all right? So yeah, that's the output that matches the input A, right? Can't give a value for A because that's a variable, so just have to say A. Now, let's evaluate f of A. So what is that output? So how do we figure out that matching output? That's where the formula is useful to you, right? Okay, that's where the equation is useful. So you know that f of x is 2x squared plus 3x minus 1, right? So f of a would be 2 times a squared minus 3a minus 1. Just substitute a for x in your function. So you get 2a squared minus 3a minus 1. That's it. You cannot simplify that any further by hand, okay? Because you don't know what the value for, specifically what the value for a is. So again, this is interpreting, this is evaluating. In this case, it's really easy. Let's make one that's a little bit harder, okay? So I'm not going to ask you to interpret this one because the interpretations at this point get kind of, they're kind of all the same, all right? So let's just evaluate this. So what is the value of f of a plus h? What is that equal to? So how do we evaluate that? Remember the formula? I want to write it down here. Was our original function. I see it right there. Yeah, 2x squared minus 3x minus 1, right? Okay. So to evaluate f of a plus h, just take the a plus h and substitute it for x in this formula. So you really just have an algebra problem here. 2 times a plus h squared minus 3 times a plus h minus 1. Now let's simplify this. This we can simplify a little by hand. So let's try carrying out some of these arithmetic operations by hand. So we have to square a plus h. So remember, do that properly. Take a plus h and multiply it by itself, right? So that in a second. What's 3 times a plus h? That's pretty easy. Minus 3 times a is minus 3a, right? Minus 3 times h is minus 3h, and then we have this lonely minus 1 there at the end. Now let's take the a plus h times the a plus h. So that's a times a is a squared. A times h is a times h. Here's h times a, which is the same as a times h. So I'm going to write it as a times h. I always like to write my variables, by the way, in alphabetical order. That helps keep them aligned properly. And then what's h times h? That's h squared, right? Now just multiply the 2 through. So you have 2a squared plus 2ah plus another 2ah plus 2h squared minus 3a minus 3h minus 1. And these two terms, the ah terms, you can add together. So let's put those together. And that's it by hand. you can't do any more of this arithmetic in this expression by hand. So this is fully simplified. As far as we can start. Wow, what a mess. Okay. But there it is. Nevertheless. Yeah, well, I kind of do have it in front of the equal sign, right? Because I have a sequence of equal marks here, right? Oh, you want to come back and put it there? I guess we could, but I don't think it's super essential because of the way I wrote all the equal marks there. Now, if you want to evaluate f of x minus 2, you need to be careful of your order of operations, all right? So go ahead and evaluate f of x and then subtract 2 from that, all right? So this first, and then subtract the minus 2, okay? So don't try to subtract the minus 2 from the x first and then evaluate f of that, okay? So what is f of x? That's so easy. It's just this, right? So there's really nothing to do here. You already know f of x is 2x squared minus 3x minus 1. And then don't forget you're subtracting 2, okay? Right. So you would end up with this. Which is slightly different from part E, okay? So you see that has to do with the positioning of the 2 with the parentheses, right? So the way you evaluate E is minus 2 is part of the input here, okay? Minus 2 is part of the input because it's in the parentheses. Here, the minus 2 was not part of the input, only the x was the input. So to evaluate f of the quantity x minus 2, you just take all of x minus 2 and substitute it for x in the formula for f. So you get 2 times x minus 2 squared minus 3 times x minus 2 minus 1. All right, see the difference? By the way, when you read these off of the page, they read the same, okay? If you read this off of the page, you would say f of x minus 2, right? If you read this, you would also say f of x minus 2. So you read them, they sound alike, okay? But, of course, they're different. Let's see, what would we end up with here when we do all of this algebraic simplification? Well, we have 2 times x minus 2 times x minus 2. I can multiply minus 3 times x minus 2 easily. That's minus 3x plus 6 minus 1. Now multiply the x minus 2 times the x minus 2. I'm going to do that quickly. You'll get x squared minus 4x plus 4. So I skipped a step there, but you can go back and fill that in. And now multiply in the 2. So you have 2x squared minus 8x plus 8 minus 3x plus 6 minus 1 is 5, right? And now the 8 and the 5 will also add together. So you get 2x squared minus 8x. Whoops. The minus, I did something else wrong here. The minus 8x and the minus 3x also add together. So you get 2x squared minus 11x plus 13. The 8 and the 5 add together. So there it is, fully simplified by hand. See, it comes out much different. So these expressions read the same off the page, but when we evaluate them, get much different. Okay, so let's stop there. We're still going to practice a little bit more with function evaluation, but I'm going to let you do a couple of them here. Okay, and but let's take a break first. So let's stop there, and we'll come back at 11:25, our usual time, and And I'll give you all a chance to do some, so you're not having to watch me do this. All right, so let me pause. Let me resume the recording. All right, so I'm going to give you all some opportunity here. Anyone need paper to write on? You don't need paper to write on, so you can write on your own paper, but I'll give you some paper. So you guys online, you need something to write with, right? Because we're going to just evaluate a couple of expressions with function notation in it, right? Just F and G here. So let's start with F. So the way you read that is 2 times F of X. This is multiplication, okay, right there, all right, but this is not multiplication, okay? So if you're going to read that off of the page, you would say something like 2 times F of X, right? But it's not reading it off the page that we're really focused on here. It's evaluating that, right? So what is that expression 2 times F of X? What is that equal to? So remember, there's the formula for F, right? Okay. And right, we had substituted F of X for Y, remember, in that original equation, right? So how do we simplify this expression 2 times F of X, right? So try that. And then once you're done with that, you can go on and look at this next one, but we'll talk about this one first, okay? There's just a subtle difference there, right? In the second expression, just the location of the 2, okay? But did you already do 2 times F of X? That would take about 30 or 45 seconds, something maybe at most, to do. You guys are also online, right? Simplify 2 times F of X, keeping in mind there's the formula at the top there for F, right? I don't think I need to step around and observe people here, okay? So just give you all a couple of seconds to that. Put something down that you think is right there. Okay, so how do you think we would evaluate this 2 times F of X? What would I write down here? Someone online can say it too. What would I write down here in starting this evaluation of 2 times F of X there? Yeah, no, it wouldn't be. You can't. The 2 is not going to hop in there with the X, right? Okay. But notice in the next expression, the 2 is already with the X, right? Okay. So maybe what you're thinking of, Amanda, is more like this. All right. So how do you think we would simplify this one? What?
The equation.
Right, just put in the expression for F of X, right? Okay, so just put in here what F of X is, which is 2x squared minus 3x minus 1. Okay, like this. And then that's real easy, right? You just multiply the 2 in to the parentheses, so you get 4x squared minus 6x minus 2. Okay. So what is, for someone who was doing that, someone who did that differently, incorrectly, all right, would you mind sharing what you did? So Amanda, you were trying to put the multiply the 2 times the X first, okay? What was your next guess?
Oh, what-
Oh, what I did, yeah, okay.
Also, I-
Oh, well, that's what we did, right? Okay, yeah, just multiplying by 2. Somebody else do something else different that was ultimately incorrect, but different there. I'm just trying to explore what you guys were what someone might have been thinking if they did it incorrectly. Yeah, Tequila. Hmm. Oh, so what did that look like there when you wrote that down? So you had what? 2 times what? 2 times 2 parentheses x squared. With x there? Yeah, okay. And then the -1. Oh, I see. Okay. So you were just kind of adding the 2 here as a coefficient, and you didn't put the 2 with the 1 though? Oh, okay. So you were kind of inserting the 2 kind of into all of these terms in this formula, right? Okay. Yeah, so that's an interesting idea, right? This is the correct one, but I can see what you were thinking, right, when you were doing that. Okay. But actually, Jaqueline, you weren't that far off, because when you multiply the 2 into the parentheses, this is sort of what's going to happen, right? Okay, you're going to get 2 times 2 times x squared. You're going to get 2 times the -3x, but you also get the 2 times the. Okay, you also get the 2 times the 1 as well. Let me remind you of something that may help you when you're evaluating function notation. Okay, that may help you carry that out a little bit better. Okay, and this is something that you're familiar with. This is the order of operations from arithmetic. All right, so frequently in arithmetic, we'll have in arithmetic where you just have numbers being combined. Okay, frequently in arithmetic, you'll have complicated expressions where you're adding and multiplying and dividing numbers. Okay, and sometimes it's confusing when you're looking at the expression, which of those operations are you supposed to do first? You know, you might have multiple operations, addition, subtraction, division, multiplication, in the same expression. Okay, and so that confusion is natural. Sometimes it's legitimate, and so mathematicians have developed a priority, right, for carrying out operations, so that we'll all come out with the same answer. We won't be each coming out with different answers, right, when we're evaluating expressions, right? So I know you guys have used the order of operations because you've all evaluated expressions properly, so you're familiar with this order of operations. Some of y'all may recall it more quickly than others, but if you have an expression that you want to simplify, that you want to carry out the arithmetic in the expression, remember, you work inside parentheses first, inside grouping symbols first. Don't have to be parentheses, it could be brackets or braces, but you work inside grouping symbols first. Okay, so do everything inside of a grouping symbol first, and then work out. You work inside out. Okay, now once you're through simplifying inside all the parentheses, all right, then next would be exponents. Exponents have a priority. Okay, even though exponents are really just multiplication, you want to simplify exponents before you do anything else. All right, next comes multiplication and division. They do not have, one does not have priority over the other. Okay, multiplication and division have equal priority because division really is multiplication, right? Okay, so multiplication and division come next. And don't think it's multiplication before division. This frequently causes errors, by the way. Okay, it's multiplication and division, they have equal priority. If you have both, if you have lots of multiplications in an expression or lots of divisions in an expression, go from left to right. Okay, so we have a left to right bias in Western culture, right? So we're gonna so we use that in mathematics too. We go from left to right. Okay, with the operations. All right, and then next is addition and subtraction, and it is not addition before subtraction, because subtraction really is addition, right? So addition and subtraction have equal priority, but they're at the bottom of the list of operations. But you proceed from left to right with addition and subtraction. Okay, now if you look at this expression, you may think, how does this order of operations help me with this expression, right? Well, you have parentheses in this expression. Okay, so the order of operations says simplify parentheses first. So first you would simplify f of x, which is 2x squared minus 3x minus 1, right? Okay, so that's why I substituted for f of x first the 2x squared minus the 3x minus 1. Okay, next comes the multiplication, which is multiply this by 2. Okay, so simplify the f of x first and then multiply in the 2. Okay, now try this one. So there the 2 is in a different spot. All right, so how do you read that off of the page, by the way? F of 2x, right? Okay, so you would read that as f of 2x, or you could say 2 times x, because that really is 2 times x, right? But mostly likely we'd just say f of 2x, right? Okay, so how do we evaluate f of 2x? Yeah, Giselle, you did that right, okay, at home, but you just need to multiply in the 2, right? So now, Giselle, try this one, f of 2x. So how's that different with the 2 in a slightly different spot? Maude, that's beautiful, but now, Maude, you need to keep simplifying, right? Because some of the arithmetic in your expression we can carry out by hand, okay? So you can keep simplifying there. I'll see what Ahmad has typed in. He started it right. Why? But he's still trying to simplify it. Okay, let's try writing this one out then. So even if you're not completely through simplifying it, you let's start it. So unfortunately, the order of operations doesn't help you a lot with this simplifying this expression. The order of operations says work inside parentheses first. So first you would try to simplify 2 times x, but there's nothing you can do with 2 times x. All right, so 2x is just 2x. You cannot simplify that by hand, right? Now you move outside of the parentheses. That's where the f is, right? So now you have f of the 2x, okay? So that would be exactly what Ahmad said. We take 2x and we substitute it for x in the formula for f. So I get 2 times 2x squared. See, I'm going to take all of the 2x and substitute it for x. So wherever I had x, I have 2x now. Minus 3 times 2x minus 1. And now see if I can simplify this. Well, I can certainly do 3 times 2x, right? That's going to be minus 6x. You still have the minus 1 there at the end. And now how do we simplify this? Now here the order of operations can help you. Okay, but in this term, when you're trying to simplify this term, what do you do first? Square. Many students will first want to multiply the 2 into the 2. Don't do that. All right. Okay. It may turn out to be this. No, it won't turn out to be the same here. Okay. So you square first because exponents come before multiplication in the order of operations. So what is 2x squared? That is 2x times itself, right? So you have 2x times 2x, which is 4x squared. So you have 2 times 4x squared minus 6x minus 1, and of course that ultimately is 8x squared minus 6x minus 1. So don't multiply the 2 in first, okay? Do the square first, okay? Otherwise, I think you end up doubling the first term, something like that, okay? So there it is, 8x squared minus 6x minus 1. That's it, okay? That's what we end up with. And you just leave it like this. That's the answer. One thing you do not want to do, students sometimes get carried away with equal marks. So sometimes on tests, the students will think they have to put an equal 0 here or something, okay? No, all right, that's not necessary. Okay, so there's your final expression. All right, now I've got a tough one. So I'm going to do this one, and then I'm going to let you do one. So here's a lot of function notation in one expression. We want to see if we can simplify this expression. So we have f of a plus h minus f of a over h. Did we already calculate f of a plus h a moment ago, though? Oh, great. Okay, so some of this I've already done. So I can use what I previously did there. This is called the difference quotient, and also plays a key role in calculus. In particular, this is going to help us understand the slopes of curves that are not straight lines. All right. This kind of looks a little bit like the slope formula, doesn't it, in the top? And because remember, this is a y value and this is a y value, right? Remember, f is substitution for y values, correct? So this is a y value minus a y value. So it kind of already, in the numerator there, kind of already smells like a slope. That's in fact where it comes from. But let's see if we can simplify this. Let's see if we can simplify this expression. So what was f of a plus h? What did we write down before? 2a squared what? Plus 4ah what? Plus 2h squared? Minus 3h. Is that right now? All right, so all right, so all of this is just f of a plus h. Okay, now I have to subtract off f of a. We already calculated f of a though too, didn't we? So let's subtract that off. Now, when you subtract off f of a, you want to subtract off all of f of a. So be sure you put that in parentheses because you need to subtract that entire quantity, right? So put that in parentheses. If you don't, you won't be subtracting the entire quantity. You'll only be subtracting part of the quantity. What was f of a? Was that 2a squared minus 3a, whoops, minus 1? So notice I put all of that in parentheses there, okay? And then all of that, big long for a numerator there, divided by h. All right, now let's see what happens here. So I have 2a squared. This is really tedious too. Whoops. Oh, did I close it? It's okay, I've got it somewhere here. Open, open, open. Let go. Ah, there we go. Okay, so if y'all have written down in your notes there, sort of what we're doing there, you're just going to start adding things together in that numerator, right? And that means you have to take the parentheses out of the numerator by distributing that minus sign. So let me see if I've got that. May have to rewrite some of this. We are gonna have to rewrite some of it. All right, so y'all remember what this was. This was 2a squared plus 4ah plus what? Plus 2h squared minus 3a minus 3h minus 1 minus in parentheses 2a squared minus 3a minus 1. All of that divided by h. And now we're going to hopefully we'll be able to combine some like terms here, but you won't get like terms until you get rid of this set of parentheses, all right? So you eliminate those parentheses by distributing the minus sign. So we get minus 2a squared plus 3a plus 1. And now do I have some terms I can add together? I sure do, right? And in fact, I have a bunch of terms that will cancel, won't they? This cancels with this, so that's perfect. This cancels with this, and I get a 1 that cancels, don't I? So, oh, this looks much nicer. We just get 4ah plus 2h squared minus 3h. Is that it? All over h. So the numerator now is simplified, but now I can simplify the fraction. Here's how. Notice my denominator is just h, but each one of these terms in the top, I'm lucky, each one of these terms in the top contains an h, right? So that means you can divide that h into all three of these terms. Let's see, what divides out then? H goes into h what? Just cancels, right? This h will cancel this h as well. And how much is h go into h squared? Once, right? So you end up with 4a, because this h is gone, plus 2h, because one of the h squareds goes, right, minus 3. There it is. Oh, see, that didn't turn out so bad at all. There is the simplified expression. It's 4a plus 2h minus 3. I think y'all can do one of those. Okay, this will be a good test for you here of evaluating function notation. So I'm going to help you with this. Got one down here picked out for you somewhere if I can get there. Oh, at last, there it is. Okay. So I have a slightly different function, but only slightly different. X squared minus x minus 1. And I want to evaluate this so-called difference quotient. I didn't use the variable a here. I just kept the variable x, but this is still a difference quotient. So I want you to evaluate f of x plus h minus f of x. F of x is easy because you already know what f of x is, right? It's x squared minus x minus. That's easy. All of that divided by h. See if you can evaluate and simplify that difference quotient. Okay, so I'm going to go around and watch you and make sure that you're writing stuff down correctly. Okay, and once you've fully simplified this, it's going to come out pretty easy. Okay, so it simplifies really nicely if you do it properly. But be careful about your negative signs. Okay, because if you start messing up the negative signs, then things won't simplify nicely. So be careful about. You got minus signs here and you got minus sign here too, right? Okay. All right. So so let me go around. People, you guys at home, right, also see if you can simplify this. F of x is easy to simplify because you know already what f of x is. This one is the tricky one. So. Wait a second. You did. But once you get, then I got it. Yes. This is the part. This means. Yeah. Two. I see what you. Oh, in you. And two. Add another thing. True. Sure. That's true. Yeah. Thanks for. Yeah, can you go back? Oh, you forgot to divide by. Oh, right. See that? So. That is. So. Still. Not distribute, so. That's what H is. Sketch. So, yeah, H over H is 1. That's it. Sure. Oh, y'all are doing. Y'all got started. You are doing really well. So, turn my slow. I think there should be a 2 somewhere there. Okay, yeah. You lost it too. Okay. All right, let's take this step by step. Y'all did really well. All right. So Giselle says, is that your suggested answer there, Giselle? 2x minus 1, or is that for a previous problem? Let's try this. Let's try this step by step, right? Well, that's the way we'll have to do it because these are complicated. So you really do have to do them kind of slowly, right? So I think the only thing that people were getting off on there, getting messed up on a little bit was the f of x plus h, okay? So that was throwing people. And I know that visually looks funny because you have the x here, and then x is also in the formula for f of x, right? Okay, but that's meaningless. You evaluate f of x plus h by taking that expression, x plus h, and substituting it for x in the formula for f, okay? So you would get x plus h squared minus x plus h minus 1. All of this is f of x plus h, right? Okay. So in evaluating function notation, what's in the parentheses is the input. So to evaluate that, you substitute it for your input variable, usually that's x, in your function formula. Okay, so take the whole thing, x plus h, and substitute it for x in the function formula. Now, but we also have minus f of x here, right? Okay, in this numerator, f of x is the formula. So where you see f of x, just put in x squared minus x minus 1, because that's what f of x is, right? It's just this expression. But since you're subtracting, be sure you put x squared minus x minus 1 in parentheses, because you want to subtract all of f of x. So let's put that in parentheses to make sure we're subtracting all of f of x. If you leave the parentheses off, you're only subtracting the x squared. Okay, but f of x has these two terms as well. Want to subtract them also. All of this divided by h. So that's really the conceptual part is finished. The rest of this is just algebra. Now the algebra can be hard enough, right? But the rest of this really is just algebra. To square x plus h, remember you just multiply it by itself, right? Minus x plus h in parentheses is easy. Just distribute the minus sign. So minus times x minus times h minus 1. Here, to get rid of these parentheses, distribute the minus sign again. So you get minus x squared plus x plus 1. Okay, that's the easy sign mistake to make at the end. still all divided by h. And now what's x plus h times x plus h? Well, you get x squared, you get an hx, you get another hx, and then you get an h squared, right? And then we have to keep writing stuff down. It's kind of tedious. These difference quotients are kind of tedious. Now, can we cancel some terms here? And we can also add some terms together, but we can also cancel some terms, right? So we get really lucky. The x squareds go away. What else goes away? The ones, the x's, right? So you don't, not much is left, right? You have hx plus hx, which is 2hx. And then plus an h squared is left, right? Is that it? No, something else has got to be in there. Oh, this minus h, right, is still in there. That's hard to see, but it's still there. And now we're going to get even luckier. We had a bunch of cancellation, so that was nice. But we get even luckier here because these three terms in the numerator all contain h. So that means I'll be able to divide out this h. If one of these terms did not contain h, I could not divide out the h. But I can divide h into all of these terms. So let's see, it divides out there. Here it goes, the square goes away, right? And what's h over h at the end? It's a 1, right? So we get 2x plus h minus 1. That's so nice there. So it really just simplifies to not a bad expression at all. 2x plus h minus 1. Wow, okay. Well, I know there's going to be 1 or 2 maybe like that one in your homework. So, so that practice will help you for when you're doing your homework. All right, let's wow. Let me show you one more thing. We've got one more. I got one more problem for y'all to do. Wow, y'all are staying busy today. This one's easier though. You will need a calculator, however. So all right, so let's look at function notation though, but let's look at it in an applied setting instead of just so abstract. So let's see, this says if a dog weighs 50 pounds on the surface of the earth, its weight, it's supposed to be a T there, its weight W at h miles above the surface is given by this formula, okay? So if it weighs 50 pounds at the surface, then its weight above the surface is going to be less. So there's the formula that you can use to calculate its weight. A certain distance above the surface, and the h here is that distance given in miles, okay? So here we're actually giving you an input variable and an output variable, but we can transform this into function notation by creating a name for this function. And because this, if you graph this expression, if you graph this formula, you'll see it is a function. And so we could use, any name for that function that we like. So, our favorite name is f for function, but we use different letter names for functions as well. What's the input variable here though? What? No, weight is what we're calculating, but what we would be given is the height, right? So the input here is the height. That is a little bit confusing when I just describe a situation to you and explain and ask you what's the input quantity and what's the output quantity. In functions, in practice, when we use functions in practice, like in this situation, usually there's a quantity that's easy for us to measure, so we'll know that quantity, and then we use the function to determine a second quantity that's harder for us to measure. So in this situation, we can, what would be easy for us to measure is the height above the surface, and what we're trying to compute that may be more difficult for us to measure is the weight, right? So the input quantity here would be the h. That's what we can measure easily. And the output quantity that's harder for us to measure is the input quantity is the height, because that's what would be easy for us to measure. And then what we were trying to compute that's harder for us to measure is weight, right? So the input quantity here is h, and the output quantity is weight. You can also sort of tell that from the way the expression is written, okay, right? Because you have w equal, usually in a function, your output quantity be equal to some expression. So, so I'm going to give f as the name of this function, and the input variable is h. The input quantity is h. Now, unfortunately, that forces us to make up a new name for the function, right? Okay, and sometimes that gets a little bit tedious to have to make up names for functions. So in mathematics, we often cheat, and we'll just use the output variable as the name of the function. So you might see this formula written as w of h instead of just w, okay? That means the weight is a function of the height, okay? And then we don't have to make up a new name for the function. So we would just say the name of this function is the same as the name of the output variable, it's w, okay? That's just a shortcut we often take in mathematics, just a lazy shortcut. With that in mind, then what is the meaning of the expression w of 100? That's what I was trying to get to here, okay? So what does that mean? Don't try to calculate it for me. What does it mean, okay? So in words, what is w100 trying to indicate? You write that down. What are you trying to say? Write down w of 100. The height is 100, right? Okay, but if you just wanted to indicate the height is 100, Amanda, you would say h equal 100. Okay, so this is more than just the height is 100. But it is true, the height is 100. This just means a little bit more than that. What, Jed?
What is the output?
Input of 100. But what's the output in this problem? The weight. So you don't have to say output. You can say, you can be more specific. You can say the weight, right? That matches the input 100. But what's the input 100 here? That's the what? That's the height, right? Okay. So we wouldn't say the height that matches, I'm sorry, the weight that matches a height of 100. That's not the way you would say that in English, right? You would say what? Or the weight at 100 miles, right? Okay, you would, that's just what you would say, correct? So the really short way to say this is the weight at 100 miles, or the weight at 100 miles above the surface, or something like that, right? Let me write that in. Does that make sense? Yeah. It is the output that matches the input of 100, but in this context, output means weight and input means height. So you can be a little bit more specific than just say, just using the generic terms output and input, you can say, oh, the weight 100 miles above the surface. That was much harder, I think, than the next problem, although you're going to have to use a calculator. So let's finish fast. What is that weight? I'm curious. So how much is that dog weighing 100 miles above the surface? I have lots of questions about this problem. I'm not sure how this formula is supposed to be working. I think the formula is valid, but I think I don't think the dog is going to experience this weight 100 miles above the surface. I think the dog's perception of their weight is going to be 0. Okay, but it's not what the formula gives. Oh yeah, you can't do this without the formula. You're right. Okay, so all right, so there's the formula. See if y'all can do this calculation for me quickly, right? Okay, we're running out of time. So we got 3 minutes. You got 3 minutes to do the calculation. I don't know the answer, right? So what is W of 100? It just means you're going to substitute 100 for H, right? Okay, so y'all do that with a calculator quickly. So let's see, I can write it down what the calculation looks like, but someone with a calculator is going to have to help me. What, approximately 47.6 Is that what other people got? Okay.
uh,
All right, so yeah, so approximately 47.6, right? So by some measure, that the weight of that dog is 47.6. Again, I don't think that's what the dog is gonna feel though. I think the dog is gonna feel weightless 100 miles above the surface, so not exactly sure how this formula is working. Okay, I don't know. All right, maybe does it say surface of the earth? Maybe it's some other surface. All right. So okay. All right. So well, we're not quite through talking about function notation and functions in general, but we're pretty far through this, and so we'll finish that next time. And then it's going to seem like we're going to something completely different, right? And now for something completely different, because we're going to start talking about angles. Seem to have nothing to do with relations and functions, but of course, in mathematics, all things are interrelated. So we're going to see how angles actually relate to the idea of relations and functions first. Okay. All right. So see y'all on Monday. You got one homework due Saturday, right? So it's only 9 problems to be able to make a good score on that. Thank you, Fernando Perez. 47.57.
On the test, can we bring extra sheets of paper to solve the problems for the equation if it's not enough space in the test?
Usually when you take the test, I mean, I usually put lots of blank space on the test, but you can use scratch paper too.
Okay, thank
Yeah,
you.
you can bring a calculator and an index card. We discussed that at the beginning of the class. That's your survival card. I need to mention that again.
Perfect. All right. See you Monday, Professor.
Bye.